Good morning everyone, and welcome to today's worked exam answer video. Today I am tackling what I genuinely believe to be one of the most difficult questions that AQA have ever created. So we're looking at an 8-mark redox titration calculation, and I'm sure you'll be able to see why it is quite so tricky as we work through it. But essentially we've got two different titrations going on, and from those two titrations we have to work out how many of those ions that are reacting in those two titrations come from one of two sources of those ions, and then do a percentage by mass calculation. It is really tricky. I will try and break it down for you as clearly and concisely as I can, but as always, if anything remains unclear by the end of the video, please do not hesitate to get in touch. So I'm going to do all my highlighting, my annotating and my worked answer, and then like I say, I'll talk you through it as best I can. Okie dokie, let's get down to business. So it tells us that the question is about compounds that contain ethane dioate ions, which are the C2O42- ions. Now a white solid that we're going to be dealing with, we're told, is a mixture of sodium ethane dioate, so Na2C2O4, which contains those ethane dioate ions. The white solid also contains ethane dioic acid dihydrate, which is H2C2O4.2H2O, which also has the ethane dioate ions, and it contains an inert solid. So we don't need to worry about that because it's inert, it's not going to react in either of the two titrations that we're going to do in a second. So that's helpful to know, but not useful for our calculations. A volumetric flask contained 1.90 grams of this solid mixture in 250 centimetres cubed of aqueous solution. So immediately we're then told we're doing two different titrations, and in each of them we're using 25. So as we're used to seeing now in back titration calculations, we're going to need to remember to scale whatever number of moles we get in each of these titrations up to the 250 centimetres cubed. Now, because we've got two different substances that both contain the same ions, the ethane dioate ions, we need to think about where these ions are going to come from in each of these two titrations. So you'll see what I mean hopefully in a second. So in the first titration, we're taking 25 centimetres cubed of the solution, adding it to an excess of sulfuric acid in a conical flask. The flask and contents were heated to 60 degrees and then titrated with a 0.02 mole per decimetre cube solution of potassium manganate 7. When 26.50 centimetres cubed, which I converted into decimetres cubed, of potassium manganate 7 had been added, the solution changed colour. They've then given us the balanced chemical equation for this reaction. Now this is a redox reaction. We've got the C2O42- ions being oxidised into CO2. We've got the MnO4- ions being reduced to Mn2+. How do I know that? One, I'm used to writing the half equations for these reactions. So if we wrote a half equation for MnO4- going to Mn2+, we would be gaining electrons on the left-hand side of the half equation, which is reduction. And if I did an oxidation half equation for C2O42- into CO2, I would see electrons being lost. Also, in terms of oxidation states, the manganese, the oxidation state decreases from +7 down to +2, and there's an increase in the oxidation state of the carbon in the C2O42- up to CO2. When we're thinking about the source of those C2O42- ions in this first titration, they can come from both of the sources of the ethane dioate ions that we have in our 1.9 grams of that white solid. So we can get these ions from the Na2C2O4, which is a salt. We can also get the C2O42- ions from the H2C2O4.2H2O, which has the ability to act as an acid, and the clue there is in the name, ethane dioic acid. I guess we should be familiar with things like this being salts, with the sodium being present if we were to draw out an ethane dioate ion, it would be C double bond O, C single bond O with a negative charge, and then repeated again, C to double bond O, C to single bond O with a negative charge, and then those Na pluses would be attracted to the O minus ions. So that would be our salt of that dicarboxylic acid. What we're then able to do, like in a normal back titration, is to use the concentration and the volume of the potassium manganate to get the moles of the potassium manganate, use the 2:5 ratio to then get the moles of the C2O42- in the 25 centimetres cubed, and then scale it up to get the number of moles in the 250 centimetres cubed, which is exactly what I did. And I've just numbered the different steps here. So step 1, step 2, step 3. I'm going to start with step 2, then we're going to do step 3, and then we're going to go back to do step 1, again, as we're used to with these calculations. So there's my working out for getting the moles of the potassium manganate from the concentration and the volume that I converted into decimeters cubed. Then using the ratio to get the moles of the C2O42- ions, and that would be the moles in 25 centimetres cubed. So to get the number of moles in 250 centimetres cubed, I need to times it by 10. So I took the 1.325 times 10 to the minus 3 and timesed it by 10. So that is how many moles we have of the ethane dioate ions in both the Na2C2O4 and the H2C2O4.2H2O. That's that total there. In the second titration, we're again using 25 centimetres cubed of the solution. We're titrating with a 0.1 mole per decimetre cube solution of sodium hydroxide using phenolphthalein as an indicator. The indicator changed colour after the addition of 10.45 centimetres cubed, which I've converted into decimetres cubed, of the sodium hydroxide solution. Again, they've given us a balanced chemical equation. Now this is acting as an acid here. This is my alkali to make a salt and water. So the C2O42- ions here now are only coming from the acid. Salts don't react with alkalis, and this was a question that came up in relation to another video that I did recently. When we're thinking about things that react with alkalis, acids are the main thing. We need to be thinking neutralization. Salts won't be able to react with alkalis. So this time, these C2O42- ions are only coming from the H2C2O4.2H2O component of the 1.90 grams. So step 3, again, use my back titration skills to work out the number of moles of sodium hydroxide, or the hydroxide ions, because they wrote an ionic equation. So concentration, volume in decimeters cubed, got my number of moles. Then I used the ratio, which is 2:1, to get the number of moles of the H2C2O4. And again, that would be the number of moles in 25 centimeters cubed. To get the number of moles in 250 centimetres cubed, I then times that by 10. So we've got 5.23 times 10 to the minus 3 moles of the C2O42- ions that only come from the acid. So if we're trying to, in this question, calculate the percentage by mass of sodium ethanoate in the white solid and give our answer to the appropriate number of significant figures, which is 3, because all of the numbers are to either 3 or, for the titration titers, 4 significant figures, and we always have to go with the lowest number of significant figures, which is 3. We need to know how many moles of the C2O42- ions are going to come from just the Na2C2O4, the sodium ethane dioate. So to figure that out, if we know the total number of those ions coming from both species, and then we know the amount of those ions that come from the acid component, we can figure out the difference, and that will tell us the number of moles of C2O42- ions that come only from the sodium ethane dioate salt, which is 8.025 times 10 to the minus 3. Then we can use the moles and the MR of the sodium ethane dioate, which is 134, to get the mass of the sodium ethane dioate in the original 1.9 grams. So we were told that 1.9 grams was made from the sodium ethane dioate, the ethane dioic acid dihydrate, and an inert solid. And what we've just been able to say is 1.80 grams of that is the sodium ethane dioate, We could, if we really wanted to, we're not asked to, but we could also use the moles of the C2O42- ions from the ethane dioic acid dihydrate, and also then use the MR to get the mass that came from that, and then we could figure out the mass of the inert solid if we were asked to, but we're not. What we're interested in is getting the percentage by mass of the sodium ethane dioate. So we know the mass of that, we know the total mass of the solid, we can times that by 100, giving our answer to 3 significant figures is 56.6%. Now, I'm sure some of you will have questions. I'm sure some of you will need to watch this through a couple of times, but the key things for me here are understanding that in the first titration, both the Na2C2O4 and the H2C2O4.2H2O provide these ions. So when we get the moles of these ions, that is the moles that come from both of those components. But in the second titration, because we're reacting those ions with an alkali, they can only come from the acid, because only the acid can react with the alkali. And that's the key to unlocking this question. After that, it just becomes quite lengthy. Lots of different calculations, lots of places to trip up with your calculations. But hopefully, seeing it set out like that, having me explain it, makes some sense. Take some time to digest it. If you do end up having questions, do not hesitate to get in touch with me. Might be easier to send them via email due to the limited number of characters you can write on TikTok comments. If that's the case, the email's in my bio, and I look forward to hearing how I can help. Thanks so much for watching, guys. Hope you have a really lovely day.